Do you hear me? Okay, hello everyone. My name is Andrei Vagin, and I work in Parallels in Linux kernel team. And today I want to tell you about checkpoint restore and online migration functionality for Linux containers. Probably many of you know that this functionality exists for a long time for virtual machines. And nowadays, many people want to use Linux containers and have the same functionality. And today I want to tell you about two projects. The first one is CRIU, checkpoint restore and Userspace, and the second one is P-hole. This project is built on top of CRIU, and this project allows to migrate containers and processes between servers. And I want to start with a brief history. At the first time, checkpoint restore functionality was implemented in OpenVZ kernel in 2005. All logic was in a kernel space, and actually this version of checkpoint restore is used in the last stable OpenVZ kernel, and we are going to move on CRIU only in the next release. After a few years, Oren Laden and his company implement the same functionality for upstream kernel, but Linux community doesn't accept this version because there are too many, because the code was too complicated, and Linux community decides that it should not be in a kernel. So in 2011, my colleague Pavel Milyanov suggests to move the most part of logic in a user space. Linux community looks at this idea with some skepticism, but accepts the kernel part. So the CRIU project was born, and we start developing. Now, how does this work? And I want to start with, let's look at the state of virtual machine. The state of virtual machine is memory content, CPU states, and the states of a few virtual devices. But if we look at containers, we can see that we need to dump namespaces, we need to dump processes. Each process has own address space, memory content, CPU states, a set of file descriptors, and a few other properties. And memory regions and file descriptors can be shared between processes, and file descriptors can have dependencies between each other. It's, for example, Unix sockets, pipes, and so on. So now I think you understand that checkpoint restore functionality for Linux containers is much more complicated than for virtual machines. And now let's look at the dump process in detail. Dump process is much more simpler than the restore process, and on this stage we need to save enough information about process to be able to restore them later. So we use all available interfaces to get this information. We use ptrace, netlink to get information about network namespaces, about sockets. We use the proc file system. And the most interesting part of dump process is parasite code. A parasite code, this technique allows to inject a specified code in arbitrary process. And we use this code to dump properties which only a process can tell about itself. We use this technique to dump memory content, to get file descriptors. And the first prototype of parasite code was developed by Tejun Hea. He is one of active Linux kernel developer. And I forgot to say that when we started CRIU, kernel doesn't didn't provide enough information about objects, so we had to expand kernel functionality in many places. Now let's look at the restore. The restore process is much more complicated than dump because we need to find a sequence of actions to restore the dumped state. And here is a few problems. And all kernel objects can be divided on a few parts, actually two. The first part is objects which can be transferred between processes. It's, for example, file descriptors. And another group of objects is objects which can be only inherited from parents. It's, for example, copy on write memory, session ID, and so on. So the restore process can be divided on a few stages. On the first stage, we restore namespaces. Then we restore processes and objects which can be only inherited from parents. Then we restore other objects, and here is one moment. On all the stages, CRIU lives in a process address space, so we can't restore memory regions on right places. So we restore memory regions on temporary places, and on the final stage, on the final stage, we use position-independent code, which we just inject in address space, execute it, and remove CRIU from address space, and do the final step, resume processes. As a first glance, it's not so easy to resume processes from defined points, but if we remember how processes return from signal handler, we can find that for this process just call sigreturn system call, and CRIU actually do the same. We construct signal frame and call sigreturn, and kernel do everything, do what we need, and the process is restarted from defined state, and all system calls are restarted just like when you return from signal handler. Now I want to tell you about integration CRIU into another project. Within first 2 years, we complete basic functionality. CRIU supports the most part of kernel objects, and about 1 year ago, we announced that we are ready for real use, and in this year, CRIU was integrated into Elixir, and it's near to be integrated into Docker. And the first question is, why do we need to integrate CRIU into other projects? And here is a problem with external resources. Actually, in many cases, process and containers has external resources. It's resources for which we can't to get complete states. So only owner know how to create these objects, and we think that if CRIU will be integrated into another project, this project will prepare all external resources and provide them to CRIU, and CRIU will restore all other stuff. At the beginning, CRIU is a command line tool, but it may be not so convenient to use command line tool from other projects, from languages. So we support RPC protocol, and library just under this protocol. We have a plugin engine to extend CRIU functionality, just in case if you want to support something specific, you can just write plugin. And we have action scripts which use for some specific actions like lock unlock network, do additional stuff for namespaces, and etc. And CRIU mostly designed for Linux developers. It's maybe hard to use for normal users. So, for example, if we look at Elixir, Elixir provides Elixir 2.2 command, which is ready for end users. And this command actually call CRIU command when it works. And now I want to move to online migration. Now when we learned how to suspend resume containers, we actually can move containers between servers without restarting processes. For that, we need to suspend container on the source host, then transfer images on the another host, and just restore this container from image files. But the size of images may be quite big, and the downtime will be too long and will be not acceptable for many cases. And our goal was to optimize this process to make downtime acceptable for many cases. And actually, we didn't invent anything new here. We just took existing idea from OpenVZ. And this idea is about dumping memory without freezing tasks. And now how we do this? We do a few iteration. On the first iteration, we just move whole memory on the remote host. Then we move only changed memory from the previous iteration. We repeat this a few times. And on the last step, we just freeze process and do full dump of process and just resume container on the remote host. For this, we had to add a memory tracker in Linux kernel. And now I want to show you a small demo. On this demo, I will create a small container with VNC server. I will execute a screen server just to see when a container will be frozen and how long it will be frozen. And I will do suspend resume without predump, and we will see how long it will be frozen. Then I will do predump and again suspend resume, and we will see that a downtime in this case will be much smaller. And now let's look at this. Here is a small script to execute a container. My container has own PID namespace and IPC namespace. We execute VNC viewer, which is connected by TCP. Now I use Python just to allocate memory. I allocate 1 GB of memory. It's a screen server, and now let's do some preparation. Just create directories for image files. Here is a process list. You can see it's the init process for this container. And here is Python and screen server. I drop caches just to avoid side effects. And now I'm going to suspend resume container, just dump and restore. And I use TCP established options just to allow to dump TCP connection. And now we see that container is frozen for 8 seconds. Now I need to update the PID of the init process because it's restored with another PID. And now I'm going to execute predump. Predump, it's a CRIU command to dump memory without freezing a container. I use the track mem options, which say that I want to track memory changes. And now we just do dump and restore. And I just said where is the previous iteration. And it's only 1.5 seconds in compare with 8 seconds in the first case. And it's much faster. And now I want, here is images for the first iteration, and you can see that here is only memory content. And here is images for the second iteration, and here are images for all kernel objects. The size of first iteration is about 1 gigabyte, and the size of the second iteration is about 50 megabytes. It's much smaller. The online migration process is not so simple, so we decided to create another project which called phole, process hole. This project is built on top of CRIU. It's written in Python, and it has two abstractions to support different storages and to support different applications like LXC, Docker, OpenVZ, and so on. And here is a scheme how it works. It do a few iterations of predump and sync file system. Then we freeze processes, sync file system. At the last time, do a full dump of containers processes, and try to restore the container on the remote host. If this operation failed, we just resume the container on the source host, and if this operation completes successfully, we just kill container on the source host. And now I want to say a few words about new features in a kernel. I want to start with features which are already used in another projects. And the first feature is a new mod for ptrace, which is called ptrace sys. This new mod for ptrace allows to handle process in stopped state, and this new mod is already used in the trace utility. And probably some of you remember that a few years ago, trace utility can't handle stopped state correctly for process, and now trace utility use ptrace sys and can do this correctly, and actually it's probably good. And we expand socket diag. Now it provides much more information about sockets, and socket diag is already used in IP route tools. And for example, now you can get a peer for the Unix socket. One more interesting feature is TCP repair mode. TCP repair mode, it's a new mode for TCP sockets, which allows to dump and restore the state of TCP connection. In this mode, we can get sequence numbers, we can get options, data from queues, and then we can create a new socket and just restore the state in this socket, and just get the socket with the same state which we have before. And in my demo, you could see VNC viewer, which was connected to VNC server, and I didn't execute VNC viewer each time again because TCP connection just was dumped and restored each time. One more feature, it's a task memory tracker or duty memory tracker. It's a key feature for online migration. And in this year, our community is growing much faster. CRIU was integrated into Canonical. A few people from Google tried to integrate CRIU in Docker. And we like to see new people in our community, so everyone is welcome. And a few numbers about our projects. We have more than 5,000 commits, more than 80,000 lines of code. It's written mostly on C. And that's all from me. Do you have questions? Yeah.
When you inject the parasite code, how do you make sure the process, when you interrupt it and save everything, how do you know that it's safe to do so?
We use, the question is actually how we inject parasite code, and we use ptrace, and we use ptrace sys. Ptrace sys just interrupt process and report its state to us, and it allows to use all usual command of ptrace. We just change registers and execute a map system call just to map some memories. Then we inject our code in this memory and just fix registers to execute this code. And at the end, we call sigreturn, and process just start from the point where it was stopped.
Safe from the point of view of the process, is it safe to interrupt the process anywhere?
Yeah, it's safe because ptrace sys just guarantee us this that it will be that we will able to resume this process from this point.
Do you provide a mechanism to update the app tables on other hosts? App problem. When you move from
The question is, do we provide some mechanism to update ARP tables on hosts? And actually, it's this functionality should not be in CRIU. This functionality should be in application. Just for example, if you use LXC containers, LXC tools just need to update ARP tables. And so. Okay.
Are there requirements for the kernel? Needs the kernel on both hosts needs to be the same, or is it possible to have different final versions, for example?
Yeah, the question is, do we need to have the same kernel on both hosts? And the answer is no. We don't need. We can use different hosts, and one of the feature for this functionality is just update your host, just do some maintains. If you want to update host, you just migrate all containers to another host, update this host, and just return containers to this host. And in OpenVZ, we have interesting functionality which allows you to reboot hosts without stopping containers. On reboot, you just suspend all containers in memory. Then you call keyexec to boot a new kernel. And we have a file system which can live after keyexec in a new kernel. It just saves between, we just create this file system before keyexec, and then we see all data which we save on this file system after keyexec. So we just speed up the process of reboot. It's very fast. Yeah.
What kind of storage does this work with? I assume there's some kind of I/O requirements.
Sorry, could you repeat?
When you migrate a host and it's doing some I/O to some shared storage system, NFS or whatever.
What kind of storage do we support? Now we support shared storages because in this case we don't to do anything. It's just the same on both hosts, and this driver is empty. And we have another driver which uses rsync. Rsync allows to copy file system iteratively. It's actually what we need. And in OpenVZ we have ploop. It's a block device which support snapshots and which is able to track changes on the device. And for online migration OpenVZ we use a tracker in ploop. So we just move storage iteratively, just like memory. Other questions? Okay, thank you.